Yes, recording has started. Hello, everyone. Thank you so much for joining us today. I'm really excited for today's talk. It gives me immense pleasure to introduce Lucas. He's currently pursuing a PhD at UFRGS, Brazil, advised by Professor Anna Bazzan and Professor Bruno, UMass. And part of his PhD was done in AI lab at BUB. He's also a part of Farama Foundation, a non-profit organization that maintains the largest open source RL libraries in the world. This summer, he's also interning at Disney Research, exploring deep RL for robotic tasks. In his PhD, he's tackling the problem of how to design sample-efficient multitasking, multi-objective reinforcement learning algorithms, which are capable of learning multiple behaviors that can be combined to solve novel problems. Thank you, Lucas, for taking your time and joining us today. Now the floor is all yours.
Oh, hi, everyone. Thank you very much for the introduction. I'm very glad to receive this invitation to give my talk here today. So basically today I'll present the preliminary work that I did so far in my PhD on sample efficient multitask and multi-objective reinforcement learning by combining multiple behaviors. So let me start with some motivation first. And the main motivation of my work is the fact that humans, when they are solving sequential decision-making problems, they have an outstanding ability to combine previously learned behaviors to quickly adapt to new tasks. So as an example, let's say someone learned to play the violin or learned to play the mandolin. So this person will probably learn how to play the electric guitar way easily. And this is because the behaviors used to press or to pick the strings, they can be combined and transfer, as playing in string instruments are tasks that share some structural similarities, right? So in the field of artificial intelligence and reinforcement learning in particular, we have obtained impressive achievements in the last few years. So we know the Go, the Mastering the Game of Go paper, right? The controlling of stratospheric balloons and so on, and many other different applications. But a long-term objective of AI is still the development of generalist and flexible agents that are capable of solving multiple tasks, each requiring agents to learn a potentially new and specialized behavior. And this is, of course, an extremely difficult problem, but it is still a long-term goal, right, which motivates our work. So the second key motivation of this work is that real-world tasks are typically composed of multiple conflicting objectives. So as an example, driving a car involves trading off speed, safety, comfort, travel time, and so on. So as an example here, we can see an agent that was trained using an RL to drive the Gran Turismo video game. And here it overly optimized for speed. So you can see it learn a very aggressive behavior where it pushes the car out of the lane, right? Because it's over optimized for speed. On the other hand, here we have a very safe behavior where the agent learned to stop when it's being overtaken by another car because it overly optimizes for safety, right? So although driving a car may seem like a single task, it actually is composed of multiple conflicting objectives, and the agent will learn a different behavior depending on how its preferences between each objective change. So this leads us to the research question of my work, which is how can we design flexible reinforcement learning agents that can, in a simple, efficient manner, adapt their behaviors to solve any given tasks, where tasks are possibly defined by multiple conflicting objectives. So here, the agents must be flexible because they must identify and employ the most suitable behavior, depending on the current task. They must be simple efficient because we want to solve tasks using as few interactions with the environment as possible. And they must be adaptive because they need to adapt their policy depending on the underlying preferences over the objectives. So to tackle this research question, we have a main hypothesis that is that we can meaningfully combine ideas and insights from two apparently disparate subfields of machine learning: multitask reinforcement learning and multi-objective RL. And we show that we can combine these ideas to design novel and principal techniques to solve this problem. So basically, we introduce novel algorithms that are multi-policy, or that is, they learn multiple policies that can empower reinforcement learning agents to, first, to carefully learn multiple behaviors, So each policy or a behavior will be specialized in a different task or in a different preferences of their objectives. And secondly, we want the agents to be able to combine previously acquired behaviors so that given a new task, they can more easily and efficiently identify solutions to those new tasks. So in our work, we identify 3 main research challenges that I'll be presenting during my talk. And each of these 3 research challenges were addressed in a different publication, in a different paper, that I invite you to take a look if you're interested. And I'll try to cover briefly each one of those 3 contributions. So the first research challenge that I want to talk about is how can we carefully construct a set of policies, such that we can combine the policies in the set and directly solve any novel tasks. So first, as I mentioned before, there are 2 important related problems in a realm. The first one is the transfer learning and multitask problem, where we typically assume that the tasks are defined by MDPs, and the tasks are sampled from some kind of distribution. And here we assume that each task is modeled with a different reward function. So it can have a reward function that rewards the agent for collecting some kinds of items. And depending on how the agent cares about each item, you have a different reward function. So in the multi-objective setting, on the other hand, instead of optimizing a single reward function at a time, the agent must identify policies that simultaneously optimize a set of conflicting objectives. So in this setting, the reward function is a vector composed of multiple reward functions, and the agent has to learn to trade off each reward component in this reward vector. And what's interesting is that although similar, these settings have been typically investigated independently. So now, before I dive into the contributions, I will briefly review some key concepts and definitions that I'll use during my talk. And the first one is sector features and generalized policy evaluation. So in the sector features framework, we typically assume that the reward function is a linear combination of some features. So if phi is a vector of features, and depending on the weights that we assign to each feature, we get a different reward function. And then the sector features of a given policy will be a vector valued value function, which denotes the expected discounted sum of each feature in the MDP. So this can be seen as some kind of Q function, where the features will play the role of the rewards. So as an example, we can have one feature that is the velocity of the agent. We can have a feature that is the energy or the distance to some particular goal. So the sector features will encode how much of each feature the agent obtained during its life when following a given policy. And the key side of this decomposition is that we can perform generalized policy evaluation, or GPE, which is a simple way to directly evaluate how well a given policy can perform given any reward function. So here, if someone gives us a different weight vector encoding a different reward function, and we want to evaluate the policy, we can simply compute the dot product between the agent's sector features and the weight vector. So this is very, very simple and very efficient. And why we want to do that is that then we can perform the generalized policy improvement, which is a way to combine behaviors coming from different policies. So let's say I have learned a policy pi1 for a task that is optimizing to collect green triangles. So pi1 is optimized for this task, and pi2 optimizes for collecting the blue squares. So I have those 2 policies, and now I want to obtain a policy that tries to collect both items at the same time. So GPI gives us exactly that. It is a very simple way to combine those policies in a zero-shot way without any further learning, and then we can obtain a new policy in a zero-shot way. So more formally, generalized policy improvement extends the fundamental policy improvement operator in reinforcement learning to the set where the agent has a set of policies. So instead of improving over a single policy, the agent improves over a set of policies by acting greedily with respect to the values of all agents' policies instead of a single policy. And the key important thing here is that the GPI theorem guarantees that this new policy will be at least as good as any of the agent's base policies. So it's a very simple way to obtain a policy that we for sure know that will be at least as good as any policy the agent may have learned in the past. So now I want to discuss a bit the other related problem, which is multi-objective RL. So as I mentioned before, in multi-objective RL, we have the same classic reinforcement learning setting, but now the reward function is a vector of different reward elements, and each element will correspond to a different objective. So the goal typically is to learn, instead of a single policy, we want to learn a set of policies such that we are guaranteed to have an optimal policy for any user preferences over the objectives. So in this example, depending on the weights that we assign to velocity or to energy efficiency, we will obtain a very different behavior in the Pareto front. So you can have a policy that learns to run very fast, while another policy tries to minimize energy efficiency, and we have this entire spectrum of behaviors to learn. And then the value function of a policy will be a linear combination of its value with respect to different objectives in this multi-objective MDP. And the last important concept that we need to define is the concept of a convex converged set, which is the optimal solution set when the preferences are linear. So more intuitively, it's the convex part of the Pareto frontier. And the key thing here that we want to take a look is that the optimal policy with respect to any convex combination of the reward functions is guaranteed to be in the CCS. So basically, this is the optimal solution set in a multi-objective RL setting. So in our main results, we try to combine these ideas from successor features and multi-objective RL to tackle the optimal policy transfer problem, which is how can we construct a set of policies such that we can combine those policies via GPI and obtain an optimal policy for any novel linearly expressible tasks. And so in our main theoretical results here, we show that we can introduce a mapping between these two settings. So let's say that we are given a base MDP, and this MDP has a vector of features phi. And then we can define a multi-objective MDP with exactly the objectives or reward functions. And we make the simple mapping of saying that each objective will correspond to a different feature. And then if we see the definition of the multi-objective action value function, and we replace the rewards by the features, we'll see that they are equivalent than the successor features of the agent with respect to the original MDP. And although this is a simple idea, we can use it then to define a CCS, but now over successor features. And our main result in this paper is that if you learn a set of policies whose successor features form the CCS, then GPI will be guaranteed to identify optimal policies for any new tasks. So this is very important because this gives us basically a solution set for the optimal policy transfer problem. But we still have the problem of how can we learn the CCS. So to solve this, we introduce a new method called successor features optimistic linear support, which is an extension of a previous multi-objective RL algorithm called OLS. So I'll try to explain briefly how the main idea of this algorithm. So in this graph, I'm showing the value function of three different policies. So the green line, the yellow line, and the blue line corresponds to the value function of three different policies as a function of the weight vector, defining the task, and how the value of those policies changes depending on the task. And the main idea here is the concept of the corner rates. So the agent can focus on training for tasks defined by corner rates. And here, corner rates are the weights in which the value functions of those policies intersect. So here I'm denoting by those black crosses here. So those will be corner rates. And the reason the agent can focus on those tasks is because here they have this property of having the optimistic maximum improvement. So it means that those are the tasks that if the agent learns to solve, it will improve the most its solution set in direction of the CCS. So this is an iterative algorithm that learns a new policy for a given corner rate, added this policy to the policy set, and then keeps doing that iteratively. And importantly, this algorithm is guaranteed to converge to a CCS in a finite number of iterations. So for instance, in one of our experiments, in the richer task, here we have 4 reward features that are proportional to the distance of this robotic arm to 4 different locations in the world. And here we train successor features using function approximation, so in a kind of a DQN style. And here we can see that the expected return of the agent with respect to the distribution of tasks is quickly reach optimal solution when we use our algorithm. It exists true even if you use GPI, which is the solid line, or if you use the best policy in the set, which is the dashed lines. So while the previous methods converge to suboptimal solutions or did not learn that fast, by using this idea of the CCS, then we can identify this optimal solution set very quickly. And finally, we also deploy this learned policy sets in a lifelong RL setting. So here, the current task weight vector changes every 10,000 time steps. And here we can see that every time the task changes, our method is capable to immediately adapt to the novel task, while previous algorithms converge to suboptimal solutions, and DQ1 has to try to solve this task from scratch, basically. So in summary, in this first contribution, we showed that we can map transfer learning problems within the susceptible features framework to an equivalent problem of multi-objective RL under linear preferences. We introduced a new algorithm called SFOS, which constructs a set of policies whose susceptible features form a CCS. And we showed that we can use this algorithm to identify optimal solutions in a zero-shot manner for any given new task. And we suppose that these theoretical and empirical findings will be relevant both to the multi-objective RL communities and also to the multitask RL communities. So this concludes the first contribution, which is a paper from SML 2022. And then we can move to the second research challenge, which is how can you learn a set of policies to solve those multi-objective RL problems, but in a sample efficient manner. So one of the main challenges in RL that we know is that it's related to the sample efficiency of those algorithms. So even state-of-the-art algorithms, they typically require thousands of environment interactions just to learn a single policy. And this problem becomes more critical in multi-objective RL because now we may need many thousands of environment interactions to learn a set of policies, one for each user preference. And this, of course, becomes infeasible very quickly in real-world settings. So for instance, in autonomous driving, healthcare, or robotics domains, where it's very expensive to collect real-world data. And then how can we learn this set of policies that covers the entire space of user preferences, but how can we learn it in a sample efficient manner? That's the second main question that I try to address. And so in this second set of contributions, we introduced two GPI-based prioritization schemes for improving sample efficiency in multi-objective RL. The first one is GPI linear support, which is a method to identify the most promising preferences to train on at each timestamp. And also it's an algorithm that is also guaranteed to identify optimal or epsilon optimal sets of policies. And the second prioritization scheme is called GPI Prioritize Dyna, which identifies relevant experiences when the agent is learning a new policy. And a nice thing is that it's the first model-based multi-objective RL that can be applied to continuous for domains with continuous states and actions. So the idea of GPI LS is similar to the previous algorithm that I showed, but so the idea is that we again learn a set of policies whose values will approximate the CCS. But the main difference here is that we can use GPI as a prioritization scheme. So again, we identify which are the most promising preferences to train on at each time step. We focus on corner rates, but now the idea is that we can prioritize the reward weights with respect to the performance improvement given by GPI. So given a set of corner rates, the agent will try to learn next the task such that it can find the maximum gap between the performance of the GPI policy and the performance of the best policy that the agent knows currently. So again, the agent, the maximum improvement again is guaranteed being one of the corner rates. But now the idea is that the agent can select the corner rates with higher GPI priority at each iteration, then it will learn an improved policy and keep repeating this process iteratively until convergence. So our algorithm GPI-LS has some interesting theoretical properties. First is that it's guaranteed to find the CCS in a finite number of iterations. And a second new contribution is that even if you're using underlying reinforcement learning algorithm that only produces epsilon optimal policies, so it may, if the algorithm is not able to find optimal policies, then this GPI-LS algorithm is guaranteed to return an epsilon CCS. that is an CCS with a maximum error of epsilon. So then we can bound the performance of this algorithm depending on the algorithm that we are using to learn policies. So the second way that we can increase sample efficiency in RL, which is a very known way, is by using model-based RL. So it's this idea of increasing sample efficiency by using a learned model of the environment. So, but one thing that we notice is that very few model-based methods explored in the multi-objective RL community. So the idea that we try here is to learn a model that not only predicts the next state, but also predicts the next reward vector. And what is nice about this is that this single model can be used to learn policies for any agent's preferences. So we don't need to learn a different model every time the agent is learning a new policy, but you can reuse the same model because it's predicting the reward vector, which is the same for every agent's preferences. So with this idea in mind, we introduced GPI prioritized DYNA, or GPI-PD, which is a model-based multi-objective RL algorithm that follows the DYNA framework. So basically, at each time step, the agent may generate simulated trajectories using its learned model instead of interacting with the real world. So those imaginary experiences can then be used to update the agent's policy, increasing its sample efficiency instead of having to interact with the real world from scratch. And again, the idea here is that we can prioritize which experiences the agent should focus when using the learned model by prioritizing those experiences with respect to the performance improvement given by the GPI. So it's similar to a prioritized experience replace scheme, but we are using a learned model, and we're trying to focus the use of the model for those experiences that are more relevant to the agent. So in our experiments, we tested our methods in 3 different multi-objective RL domains. The first is a classic one called Ipsy Treasure, where the agent has to trade off between collecting a treasure, which is more valued when it's in the bottom of the grid word, and also has to minimize a time penalty. The second domain is Minecart, where the agent can collect 2 different kinds of ores in the map, and it also has to minimize fuel consumption. And the third environment is a multi-objective version of the Hopper domain, where the agent has to trade off running as fast as possible with jumping as high as possible. So we evaluated the algorithms with respect to expected utility, which is the expected performance of the agent over the expected value of distribution sampled from the weight vector distribution, and also maximum utility loss, which is the maximum distance of the agent to the optimal policy for any given reward weight. So here we can see the blue line corresponds to GPI-LS, our first algorithm, while the red line corresponds to GPI-LS using GPI-PD also, so the model-based version of the algorithm. And you can see that both methods consistently identify near optimal solutions for both metrics. And those performance metrics strictly dominate that of the competitors. So in the multi-objective Hopper domain, then we also achieve higher expected utility and converge to better solutions. Again, when you use a model of the environment, so GPI-LS using GPI-PD, we obtain improved sample efficiency. And a very interesting thing here is that our algorithms require 10 times fewer environment interactions when compared to a previous state-of-the-art method called PGMOR. We also can observe the Pareto front identified by our algorithms, and you can see that it can learn a very dense spectrum of different behaviors. So for instance, policies that try to run as fast as possible, while some other policies are just trying to maximize its position in the z-axis, right? So you can see that when you use the model, we can find a more dense Pareto front than only the model-free version. And both Pareto fronts dominate the Pareto front identified by previous algorithms. Lastly, we were able to scale GPI-LS to image-based tasks. So we employed the GPI-LS algorithm into the multi-objective version of the Super Mario Brothers video game, where you have 5 different objectives. And here I'm showing the behavior learned when the agent only prioritizes time. So it's just trying to move as fast as possible in the map. While here I show an agent that prioritizes killing enemies. So you can see that the agent stops in the pipe so that it can jump in the head of the 2 Goombas and maximize the killing enemies reward. We can also identify different behaviors. So here we have an agent that is prioritizing collecting coins. So it's trying to jump in the blocks to collect those coins. And while an agent that did not care about the coins would just run as fast as possible to the right in the map. So here you can see that many different problems are multi-objective, and you will have like very different behaviors that we can achieve when you employ our proposed algorithms. So in summary, for the second contribution, we introduced 2 principal GPI-based prioritization methods with some interesting guarantees of monotonically improving the quality of the set of policies and converging to a CCS. We introduced the first model-based multi-objective RL algorithm for continuous state domains. And we showed that those methods were able to outperform previous state-of-the-art algorithms and significantly improve the sample efficiency of a multi-objective RL. So this concludes the second set of algorithm contributions that I wanted to introduce in this talk. And we can move to the third research challenge, which is how can we leverage approximate models of the environment to improve zero-shot policy transfer. So I have just shown a way that we can use a learned model to increase sample efficiency, but is there a way that we can use the model not only for increasing sample efficiency, but also for improving the zero-shot performance of the agent in novel tasks? So let's first briefly recall the zero-shot transfer setting in RL. So let's say the agent has had time to learn to solve a set of training tasks. So here the agent has to move a block in a table using the robotic arm. And then the agent's given a new task. So a new task that the agent has never seen before. So here the agent has to move the block away from the table. And the agent has to learn to solve this new task, but without using any new interactions with the environment, right? No further learning. And in this setting, we are partially motivated by the fact that many state-of-the-art model-based RL algorithms, they adapt poorly to reward changes. So in this plot, for instance, we can see that the state-of-the-art algorithm Dreamer, it has a large optimality gap in the setting where the reward function keeps changing over the learning horizon. So this is a big problem for multi-objective for model-based RL methods because they need to adapt to those reward changes in zero-shot RL. So to tackle this problem, we introduced a multi-step extension of GPI, which so our method performs H planning steps using an approximate model, and then it employs zero-shot GPI in all states that are reachable in H time steps. So this method can be seen as interpolation between model-free GPI and fully model-based planning methods as a function of the planning horizon H. So intuitively, you can see the HPI policy as a combination of an online planning part and the GPI part. So in the online planning part, the agent, given the current state, it will use some approximate model of the world and it can use any online planning algorithm to plan for H time steps. And then based on all states that are reachable in H time steps, the agent can use its set of policies and try to infer the estimated future returns that it could get by following any of those policies. So then he can basically employ GPI in very many different states that are reachable in H steps. And what is nice here is that if we set the planning horizon to 0, then we obtain GPI back. So the method becomes equivalent to a standard GPI. And as the planning horizon goes to infinity, then the method becomes a fully model-based planning algorithm that only selects the action using the model. We also show some theoretical results characterizing the performance lower bound of this policy with respect to the planning horizon and the action value function errors, and also errors in the model, so errors in the transition function or in the reward function. So first, if we have no approximation errors, then we get back the GPI theorem, which says that the AGPI policy will be at least as good than any of the base policies. If we increase the planning horizon, then the impact of value function approximation errors decreases because the agent will rely more on the model. But as we increase the planning horizon, then the impact of the model errors increases. So the agent will be more reliant in the accuracies in the model. So, but how can we employ AGPI in a zero-shot transfer setting? So our goal here is to solve any task in a zero-shot manner. And similar as before, we are interested in all tasks that can be represented via a linear combination of some reward features. And then the key idea here, again, instead we need to learn only a single model of the next state and a model of the reward features. So implicitly, this means that this model can induce all models with respect to all possible reward functions, all possible linear reward functions, right? So again, we don't need to learn a set of models. We can perform zero-shot transfer using a single model of the environment. So here in the for room domain, we can see the HGPI using different values for the planning horizon. Typically, it's starting to improve. It's even better as we increase the planning horizon. And we compare it with an MPC baseline, so a model predictive controller algorithm. And you can see that HPI was able to outperform it using 10 times fewer planning steps. And we can also see a very big performance improvement when we compare HPI to standard GPI. So this is in a tabular domain, the for-room domain, but you also employ a domain with high dimensional states, so this robotic fetch-push arm. And again, we can see that HPI was able to outperform previous both purely model-based algorithms and purely GPI-based algorithms under all values of planning horizons that were tested. So in summary, for this third contribution in my talk, we introduced a multi-step extension of GPI, which interpolates between model-free policy transfer and fully model-based planning. We showed that we can exploit approximate models of the environment to solve tasks in a zero-shot manner. We also showed some formal bounds of how the planning horizon trades off approximation errors in the agent's model versus approximation errors in the action value functions. And we showed that this method was able to outperform standard GPI and previous state-of-the-art algorithms, while also being less susceptible to value function approximation errors, and in both tabular and dipole settings. So this concludes the third theoretical and algorithm contribution that I wanted to discuss. This was a recent paper that I presented at NeurIPS 2023. If anyone has any questions about those papers, I'll be very happy to answer. So, but before I finish my talk, I would like to discuss some open source contributions that I have worked on during my PhD. So I just talk a bit about some algorithm and theoretical contributions in those three different papers. And now I want to also briefly talk about a different work that we presented at NeurIPS 2023 in the data sets and benchmarks track, which is a toolkit for reliable benchmarking and research in multi-objective reinforcement learning. So this was a joint work with Florian Felten and also our supervisors from the VUB in Brussels, the University of Luxembourg, the University of Massachusetts. Also, I would like to thank the Farama Foundation, which we are also part of. And so this was very an effort of a large number of people. So to motivate a bit why this particular toolkit is relevant is that I think many of you are aware of many challenges in reinforcement learning research. So first, we lack standardized environments. So it's common that each different paper use a different version of some environment, We also usually lack open and maintained code of algorithm. So sometimes you cannot find the implementation of the authors for some algorithms. Many times details are not well reported, so we don't have the hyperparameters. We are not aware of some code level optimization tricks, and is also typically very costly to train algorithms from scratch. So in summary, reproduction seems to be a very hard problem to achieve in practice in reinforcement learning. And to tackle this problem in multi-objective RL, we introduced a set of open source contributions. The first is homogenization, which is a set of multi-objective reinforcement learning environments under a unified API. The second contribution is multi-objective RL baselines, which is a set of multi-objective reinforcement learning algorithms, which are compatible with homogenization. And finally, we also introduce a benchmark containing a data set of different training metrics, multi-objective training metrics of many multi-objective RL algorithms in all environments available on homogenization. So regarding homogenization, it has a standard API which extends Genation API. So I think if you do reinforcement learning research, you are aware of Genations, which is now currently maintaining, which was previously known as Gen, which is now named Genations, which is maintained by the Farama Foundation, which I also happily part of. And we also maintain many different libraries for reinforcement learning research. Currently, we have over 20 different multi-objective reinforcement learning environments available, ranging from grid word tasks, robotic tasks, video games. So we have very different environments that we can use to evaluate multi-objective algorithms. We also have specific wrappers for those environments. And if anyone is interested, it can be easily installed via pip. And so pip install homogenization, and you can easily try to use those environments in your research. So we also, me and Florian also introduced multi-objective RL baselines, which is a library of objective RL algorithms. We try to maintain a library clean with tested and maintained code. We also have automated logging and metrics to weights and biases, and many utilities that you can use for designing new multi-objective RL algorithms. You can also find their GPILS and GPIPD, so the algorithms that I presented before are available there, so you can use to solve your multi-objective RL problem. And then to evaluate both libraries, we basically run all algorithms available on multi-objective RL baselines on all environments available on homogenization. So we have a weights and biases dashboard, which is openly available. Anyone can check the Pareto fronts identified by each algorithm in each environment. We have a tracked code version and hyperparameters used for every algorithm. And one also thing that is very nice is that those results are integrated into OpenRL benchmark, which is also an initiative for collecting results of reinforcement learning algorithms in a set of different reinforcement learning benchmarks. So you can also find multi-objective RL baselines and OpenRL benchmark. So to conclude in this talk, I try to present a bit of a general framework with formal guarantees for learning sets of policies for solving both multitask and multi-objective RL problems. We showed how we can combine those policies for solving new tasks in a zero-shot manner. We also introduced an open source toolkit for reliable multi-objective RL research. And I hope this is a small step towards flexible, simple-efficient, and adaptive reinforcement learning agents. Thank you very much for the attention, for the invitation again, and I will be very happy to answer any questions that you may have.
Now, floor is open to Q&A. If you have any questions, you can unmute yourself, open your openly ask questions to the speaker.
Hello, Lucas. Can you hear me?
Yes. Hello.
Thank you so much for your talk, and also for, I think that are super nice contributions. Regarding the CCS paper, have you looked into the questions of building a minimal basis of policies? Because I'm familiar with your paper, and I have read I have gone through the results, and it seems that in many, or at least in some environments, you don't need a CCS to fully represent the whole space of solutions. So is that something that you have in mind, or you know how to approach this problem?
Yeah, thank you very much for this question. Actually, it is a very interesting point. So I have some, I think some results that are actually in the appendix of the paper. So for instance, for Deep Sea Treasure, we have the actual CCS of this problem has 10 optimal policies. And as you correctly mentioned, so our algorithm is actually able to encode the CCS using only 3 policies instead of 10 policies, right? So here the black crosses are the policies in the CCS, the blue triangles are the policies learned by our algorithm, and the red points are all policies identified using GPI. So you can see that indeed we don't need to learn the entire CCS, right? We only learn, sometimes you only need to learn a few of policies in the CCS because GPI will identify the rest of the policies. So this is true for most of the tasks, but unfortunately, there are counterexamples where this may not work, unfortunately. But so it's not possible to, I think, to prove theoretically that you can always learn a minimal set. But for many of these tasks, empirically, we can see, same as here, that we can find a solution set that is smaller than the CCS. And it's nice to ask because I'm currently trying to tackle this exact same problem. So in my next projects.
Okay, thank you so much.
I have a question. You talked about model-based methods, right? Have you used ensemble of models or a single model?
Just let me show my slides again.
Yeah, sure.
Oops. Okay, it's at the end of my talk. Sorry. So here, yes. So in our AMAS papers, also in the HPI paper, we use a stochastic mixture of dynamics models. So basically an ensemble, a bootstrap ensemble, which are parameterized using multivariate Gaussian distributions. So this is typically what people have been using in standard RL. So MBPO, which is a state-of-the-art model-based RL algorithm for the single objective case, we use this kind of models. So we basically extended these types of models to the multi-objective case. So instead of predicting a scalar reward, it predicts a vector of reward functions. But yes, we use the same kind of models that people have been typically using in standard RL.
Yeah, that makes sense. Yeah. All right. And then, like, I could. Can you show me your third work? It's a like it's a combination of model free and model based, right?
Yeah. So here for example, right.
And this the H planning steps, is it constant? Is it variable? How are you doing it? Because as I have actually gone through MBPO paper, basically they do a short more horizon rollouts.
Mm-hmm.
Like if you roll out a lot, more, like, more than like instead of doing a short horizon rollouts, if you do long horizon rollouts, you tend to make mistakes modeling due to modeling inaccuracies, and then it compound, right?
Yeah, that's a great point. So one of the motivations actually of HPI is that we can do short rollouts, right? So like indeed, if you have very long horizons, the errors in the model compound, right? So what you can see from our experiments, for instance, is that the fact that the HPI is bootstrapping using GPI in all states that are reachable in 8 steps, it's not relying that much in the model. So I think that's one of the reasons that it can outperform purely model-based algorithms. So here, for example, so if you have a model predict controller that plans for 15 time steps, it will probably accumulate many errors. While HPI, you can use very short rollouts. So here, even for a rollout of size 2 or 3 or 4, which is very small, you can see a large improvement when compared to standard GPI. So that's the nice thing about combining model-based and model-free, is that you can use the model-free RL component to minimize this problem of compounding errors of model-based RL.
Right, interesting. Do you guys have any more questions?
Hey, can you hear me?
Yes.
Hi. Yeah. So I've been looking at the multi-objective problem for quite a while, and actually, I really appreciate the work you did with the MO gymnasium. So, one of the problems that I was trying to think of, when doing research in the multi-objective RL is whether these algorithms can scale beyond just static environments. So, like in the case of multiple environments and multiple NDPs. So, yeah, I've been looking into this problem for a while, but I'm being kind of stuck. So, just want to get more opinions. I kind of started this work only after I listened to Anne's talk at AMAS just last month. Yeah. So I just want to get your opinion. So like in multiple NDP, do you think the case of the convexity of the induced value function, will it still hold? And whether do you think the current algorithms can scale to multiple environments in multi-objective?
Let me see if I understand correctly. You mean if we have the transition dynamics of the multi-objective NDP being able to change? Is that what you mean?
Yeah. So like for example, just a simple case where like for example, in a domain randomization case where you randomize your environment over every step, and then we want the algorithm to learn maybe a expectation based optimality, or maybe just a robust optimality where it optimizes for the worst case scenario. So do you think these algorithms will be able to converge or even learn something meaningful?
Yeah, that's actually a very interesting research direction, in my opinion. So there's a lot of literature on this problem for the single objective case, right? To have many algorithms that try to learn policies for that are robust to changes in the transition dynamics. But I'm not aware of anyone that has tried to do the same for multi-objective RL. My intuition is that I don't see why it would not work. I think many of those algorithms for the single objective case, they possibly can be extended to the multi-objective RL case. Yeah, I think that's a very interesting direction. I think that probably no one has tried that yet, which is so a very open problem. And I think it's very interesting also to check how for instance, the Pareto front will change, right, if the transition dynamics changes.
Right. So sorry to interrupt. Yeah. So one of the things I tried was adapting the MO gymnasium to include a randomized environment parameters at every time step. And what I found is that actually for because of limitations in terms of compute, I've only been testing it on CapQL. And what I test on CapQL is that actually the policy degenerates and it actually doesn't learn anything its hypervolume kind of just stays near the origin, so it doesn't actually improve much. So yeah, I mean, I was just quite perplexed why that's the case. But then what I found, like just internally within the multi-objective space, is just that there's also certain problems, like in the case where you guys don't normalize each reward scale. So actually, for example, environments like the multi-objective hopper and the multi-objective cheetah actually is kind of dominated just by one reward dimension. So it kind of just it's kind of like you guys are using multi-objective algorithms, but actually the problem statement in itself, because of how the scale of one dimension is so much bigger, it kind of reduces back to a single objective problem, doesn't it?
I think I see what you mean. Yeah, I think if you have a very different magnitudes, then you can have some kind of an asymmetric Pareto front, right? Maybe you have one objective dominating all the other objectives. This is not. I think this is not the case for the environments that we have, currently in Imagination. But I see that being a problem in the setting that the dynamics changes, right? Because then also the returns depending on the dynamics, which makes things harder. But yeah, I would suggest you to actually first try some algorithm for the single objective case. And when you're sure that works, then you can include more objectives. So just to be sure that the problem is not on the multi-objective part, but maybe it's in the algorithm that you're using for the changes in the dynamics.
Right. Thank you for the advice, and thank you for sharing this talk. If you'll be happy to chat after this talk, because personally I'm still a undergraduate researcher trying to get into the multi-objective space. So if we are happy to chat after this talk and then provide advice and also perhaps collaborate on the same research direction, I'll be happy to talk as well.
Sure, I'm glad for the interest. You can maybe send me an email. I'll be happy to come up with some meeting maybe.
All right. Is there any way I can find your email? Oh, I'll look it up through.
Yeah, I'm gonna text you. I'll post it on Discord. Anyways.
All right. Thank you so much. All right. Thank you, Lucas.
Thank you.
Any more questions? If no one has any questions, we can actually wrap up the session. And thank Lucas for giving the talk.
Thank you very much. Yeah, it was. I'm very glad to present my work here today. Thanks for the invitation.
Thank you, Lucas.
This is awesome.
Thank you.